Hey kids, Dr. Division here, and today I'm going to do the Hardy-Weinberg Equations. I'll even let you tag along, and that should get you giddier than old Mr. Jacklin when he catches eye of that old Times Hard Record sports page. Alright kids, let's get in there. Alright kids, today we're going to tackle the Hardy-Weinberg Equations, which are a very special set of two equations that us, as biologists, will use to track allele frequencies throughout a population. Now, there is one rule that we must follow when using these very special equations, and that is that the population must be in what is known as Hardy-Weinberg equilibrium. Now, there are 5 distinct characteristics of the population that must be met for us to go ahead and use our Hardy-Weinberg equations. After the break, kids, I'm going to show you just a little bit more about that tricky equilibrium and how you can make sure your population is in it. Alright kids, here you can see we have the 5 characteristics of a population that is in Hardy-Weinberg equilibrium. Number 1, no random mutations. The genes are all staying the same. Number 2, no sexual selection, which means no one allele will be favored over any other. 3, no natural selection. Again, every allele is treated the same. 4th, no immigration or emigration, which means the population is not gaining or losing any individuals. Finally, we need a large population size. We need a lot of test subjects. Also, as one final note, you'll notice that we have changed the spelling of Weinberg from our first two scenes. Now, my assistant, Mr. Rose, and his terrible spelling skills, was kind enough to spell it wrong. Now, I don't want to mislead you kids, so luckily, me and my dictionary of truth were able to figure out the correct spelling of Weinberg, and we've put it for you right here. Now remember, from here on out, it will be Weinberg, W-E-I, instead of however Mr. Rose and his devilish spelling tricks spelled it before. Alright kids, coming up next, we're going to try the Hardy-Weinberg equations. Alright kids, I've written here for you the 2 equations that make up the Hardy-Weinberg equation set. Now our first one deals with the genotype of our population, the genotype. So that is the actual alleles themselves. P is equal to the frequency in decimal of the dominant allele. Make sure you keep that straight. These are the alleles we're speaking about. Whereas Q is the recessive allele. Now we're going to add up the 2 decimal values that represent frequency, and we're going to equal 1. So that's how we spend our first equation. Now, moving on to our second equation. This relates to the phenotypes, or the expressed trait. P squared represents, again in decimal, the frequency of the homozygous dominant individuals. Moving along, 2pq is equal to the heterozygous dominant individuals. And finally, q squared is equal to the recessive homozygous individuals. Now remember, all of these are the decimal form of the frequency of the population. We're going to add them up, and it's going to equal 1. Now, those are the basics of these 2 equations. We're going to go ahead and try an example, and I'll talk you through the nuances, the subtleties, the important details that you need to remember as you do your Hardy-Weinberg equation sets. Alright kids, coming up. Alright kids, here we go. Dr. Division has given you an example problem to try. I'll read it to you now. A population of 1,000 orange-bottomed baboons has only 146 individuals who display the recessive trait of a hairless bottom. Awfully smooth. What is the number of individuals who are heterozygous for this trait? Now, our first step is to just go ahead and figure out the percentage of the population who are recessive. Here we go. We're going to go ahead and divide 146 into 1,000, and we get 0.146. Now, any guesses as to what that value represents? Well, I'll tell you. It is q squared. It's q squared. That's what it is. It's q squared. All right. So q squared is equal to 0.146. Now, once we've done that, our second step is going to be to turn that q squared value into a q value so that we can use it in our P plus Q equation. Here we go. What we're going to do is we're going to take the square root of both sides, square it, and square it, which gives, whoa, what a crazy edit. Anyways, our Q value, after taking the square root of our Q squared value, is equal to 0.382. So our Q is equal to 0.832. Now remember that, after the break, we're going to figure out what our next step is, and we're going to go from here. Alright kids, hold on a second. Alright kids, we're back. We've got a Q value of 0.382. Now that Q is equal to the frequency of the recessive allele. Remember, keep that straight. Now we're going to plug it into this equation here, which is P plus, I'm just going to switch over, I'm already, 0.382 is equal to 1. Let's go ahead and subtract 0.382 from both sides. This is basic algebra now. If you had Miss Wojcik, shouldn't be an issue. And we find that our P value is equal to 0.618. So 0.618. Now we have both the frequency of the recessive allele and of the dominant allele. Now remember, all we had to start was the frequency of the recessive phenotype in the population, and as a matter of fact, that's all you ever need to start a Hardy-Weinberg equation problem. Now we're going to go on to our next step here. Remember what the point of the question was. It was to find out the number of individuals that are heterozygous for butt hair. So let's get in there. Let's see what's happening. Now we have our P, we have our Q. Let's go ahead and let's do some math. Now, I've never been very good at arithmetic, so I'm going to go ahead and take a break here. Me and my assistant, we'll do some math, we'll figure it out, and we'll get right back to you. Alright kids, my lovely assistant and I have done the math, and we've laid it out here for you. Our P squared value, which is the frequency of homozygous dominant individuals in the population, is 0.381, and again, we got that by squaring the P value here that we got from our first equation. Next up, 2PQ. Remember, this represents the frequency of heterozygous individuals in the population. Here we go, 0.472, and that was found by multiplying the Q value, the P value, and the number 2. 2 is the constant, put it in there, or you're going to be wrong. Alright, next up, Q squared, that's our final value. We got it by squaring our Q value, and it is equivalent to 0.146. Now, astute viewers will notice that it doesn't quite equal 1. It equals 0.999152. Now, that might scare you. It shouldn't. That's close enough to 1 that we're going to let it slide. Remember, we're rounding to 3 decimal places here, so we're going to have a little bit of what is known as rounding error. Not too much, just enough, we're good. So, remember, the original problem, the goal of it, was to find out the number of individuals out of the 1,000 that will have the heterozygous genotype, alright, which would represent a dominant phenotype. So, the last step, the very last step here, is to multiply 1,000 by the frequency that we found by 0.472. And the great part about using a population of 1,000 is the math is easy. So that is going to equal 472 individuals that are heterozygous for butt hair, which means they're going to have some hairy butts. They're orange baboons. They don't care. They're living in the jungles. Keeps them warm, keeps them safe. They like it. So kids, what we've done here is a basic example of Hardy-Weinberg. But the great thing about Hardy-Weinberg is they're all basic. It doesn't get hard. It's like a white girl at Starbucks, man. It's basic. Alright kids, here we go. That's all you gotta know. Just memorize. Boom and boom. And don't you dare forget about the 5 characteristics of Hardy-Weinberg equilibrium. Now if you keep these 7 simple things in mind, and you know how to do arithmetic, unlike Mr. Rose, you'll be fine. Alright kids? Don't fret about Hardy-Weinberg. Be confident. Be bold. Be a positive influence in your community. All right, kids. I've been Dr. Division here. You have a nice night.